Welcome to this brief video in which I'm going to tell you how you can generate random numbers in R and why you might like to do that. So, why random numbers? In the context of quantitative research, we need them for randomization in experiments, but more importantly for the purpose of this course, we need them to estimate sampling error. And we need to estimate sampling error to figure out how confident we can be in our conclusions from any study. In statistics, the generation of random numbers is generally conceptualized as drawing numbers out of an urn. It's quite a helpful picture to understand some of the procedures that we're going to encounter in the future. So we have this urn, we have numbers in it, and then R uses complex maths to create a pseudo-random list of numbers, which we should just treat as random, to then pick specific items out of the urn. What we need to define though is what items there should be inside the urn. And there are different distributions that might be appropriate in different circumstances. So the most straightforward one would be a uniform distribution, where basically we have all numbers between two endpoints in the urn and all of them in the same quantity, so just once. That's probably what we would use for randomization, that's what we might use to generate an order. It doesn't describe many of the processes that we could study. Most of the time when we try to simulate a sample, a different distribution would be more appropriate. So one would be the binomial distribution. And that's basically any distribution that's generated by a process where there is a specific probability for successes and failures. So for example, when we study how to toss a coin, a binomial distribution would help us to establish how many heads and how many tails we should expect. A similar distribution could model how many shots a basketball player is likely to make from the free throw line. So if we simulate any such process, also voter choice, for example, we should use the binomial distribution to decide what goes into the urn for randomization. Lastly, a lot of processes can be modeled with a normal distribution, which we'll explore in more detail in 2 weeks' time. But basically any process that has an average around which values fluctuate randomly should be modeled with the normal distribution. Typical examples would be height, weight, and so on. For each of these possible distributions, R has specific functions to let us generate random numbers. If we have a uniform distribution, there are two different functions. Which one we use depends on whether we want whole numbers or whether we want any possible numbers, including fractions. Let's first think about whole numbers. Whole numbers are where the notion of drawing balls from an urn makes the most intuitive sense, and that's exactly what the sample function does. The sample function gets a set of items, in this case the numbers from 1 to 5, and then we tell it to take 10 items out of that list and to replace them each time, because the second number should still be drawn out of the whole set from 1 to 5. For everything that's not discrete, so for all continuous outcomes, we can use these specific functions for specific distributions. So we have RUnif for the uniform distribution. And you can see the syntax here. We basically need to specify how many numbers we want and what the range of the numbers should be. For the binomial distribution, we have the rbinom function, where we now need to specify how many samples we want and how big each sample is to be. So for the other video where I simulated samples of electoral polls, a simulated 1,000 samples of a size of 100 voters each. And then we have the probability of an outcome, which in the case of the coin toss here would be 0.5. In the case of the vote, it would be the support across the population that we simulate the samples from. And then for normal, we have our norm. A normal distribution is characterized by a mean and by a standard deviation, which for intelligence happen to be very nicely defined. The mean is 100, the standard deviation is 15. So with this code here, I could simulate 10 IQ scores. The point of all this is then to see across many of these samples how much they vary, so that we can estimate sampling error. We'll get into that in class. We might want to set a random seed. What does that mean? Well, random numbers, by definition, will be different every time we generate them. However, that can be quite difficult when we're trying to learn together and everyone always gets different numbers, or when you're trying to write up your research and every time you rerun the analysis, all the specific numbers change. That's why you can use the setSeed function to define the starting point for the random number generator. And whenever you do that, it will give you the same set of random numbers following from there. So a good practice could be to actually create one random number at the start of your project and then use that random number as the seed for the project that then stays the same for as long as you're working on it. At times, you can do that. In your homework for the exams, you will be given seeds to set so that everyone actually arrives at the same numbers. So, just a couple of key concepts to remember. I can generate random numbers, and that's helpful for randomization experiments and for estimating sampling error. Don't worry if you don't yet understand why estimating the sampling error is relevant. We will practice that and discuss that together in class. Statisticians use this model of drawing balls from an urn. That can help as a mental model for what we are doing throughout these random analyses. But before you can meaningfully generate random numbers, you need to think about an appropriate distribution. So what do I expect the distribution to be like? Should each number be equally likely? Do my numbers come from specific trials where a coin might land on head or tail, or where I might pick out a Lipton voter or someone else, for example? Or does it come from a normal distribution, which are distributions that have a mean and then random variation around the mean? Please do bring any questions around that you might have to class, and I'll see you there.